Okay, so today I am going to um, here we go. Sorry. Start the last part of chapter one, which deals with proofs, mathematical proofs. And I'm going to do just one very little bit on slides, and then I'm going to move to the whiteboard and do tons of examples. That's basically what this is going to be. Um, the more exercises you do, the better, obviously. Now, the thing is with this is probably kind of new, so I would highly recommend, although I know that it's going to be even more complicated than usually. Um, but try to show me what you're doing. So what I might do next week is actually give you a little quiz, which will also allow us to um, practice or test or the test environment. You'll see how it works, although you've probably seen it before. But we'll do that. So we'll do a little quiz. But if you want to show me, will it count for marks? Yes, 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 yes. Not many marks, but it will. Um, but if you want to send me some stuff that you are proofs that you're writing up, and you want me to tell you if they're right or not, or can you repeat when the quiz will be? Yeah, I just decided this right on the spot. So let's decide that it is uh, Tuesday of next week, unless there's an objection. Um, yeah, that's what I mean. Yeah, by test environment, I mean, yeah, the whole procedure. If by some incredible chance someone has never done it, you'll see how it works. But I guess everybody's done it. So forget that comment. If you've all submitted a test using a PDF scan, then oh yeah, I didn't mean there was an different electronic environment. That's yeah, Tuesday the 16th. I guess that must be it. Yes, that's the 16th. Okay, so let's do that. I'll write it here, and you'll see it in a few minutes. Quiz Tuesday. It's like a 10-15 minute thing, right? But I'll give you more time, obviously, because you have to transfer. But it'll be a short quiz, just just to see how you're handling the proofs and all that. We'll do that. Okay. I'll send you an announcement by Mio anyway. You'll get everything. Questions, comments before we plunge? Okay, so so I'm gonna just do a couple of slides here. I'm not actually. Oh, by the way, I've modified the slides slightly. That I had uploaded them a couple of hours, but I just changed them just 2 minutes ago. Um, and the very last part in these slides I will do next time. I don't want to do all of them. But so here's a high level introduction of what we're trying to do here. So first thing you should know is that math is proofs. It's the same. I mean, that's what math is. Okay. So the all of mathematics is built on the notion of proof. And unfortunately, the impression you got from all the math you've done up to this point is that it's not at all like that. Um, when I was a kid, we did, and most kids did until fairly recently, we did a little bit of proofs in high school. We did Euclidean geometry. Um, Somehow that didn't really help me for later, just a little bit. So I'm not sure it does make a difference. But now you don't even see them, or most of you probably have never seen formal proofs in any sort of serious way. Um, but that's what math is. Okay, so basically you have to establish the truth of statements with an argument, a valid argument. Okay. There are three main ingredients in a proof. I'll get back to that in just a sec. There are axioms. So these are statements which we assume to be true. If that bothers you, I'm going to show you in just a few minutes what I mean, more precisely by axioms. Um, you'll see exactly what I mean by that. The second ingredient is previously proved statements. Once you've proved something and you know it's true, then you can reuse it, obviously. And the third is rules of inference. That actually is what will allow you to go from previously proved statements and axioms to create new statements, new proofs of statements that you did not know before that they were true. Um, now, we've done first order logic the last couple of weeks. You can write formal proofs in first order logic, but nobody wants to read that. It's like reading code. It's really painful. It's just, you don't want to do something like that. So there's a level of informality that we use in proofs. And obviously that's what we're going to do here. Now, of course, the tricky part now that we're not going to do this long enough for you to really get the hang of it. I mean, we're going to do some, but it's hard. It'll be hard sometimes to know, do I have to prove that or not, right? So how informal do we have to be? That's part of, unfortunately, part of the game. Okay, so we'll have to see as we go along what is okay and what's not okay. You'll quickly get most, I mean, a good feeling for it, but okay. Um, okay, so a bit more precisely what a proof is, and I should add a word in there. It's not just a sequence of statements, it's actually a finite sequence of statements. A proof is finite. It's a finite sequence of statements, one after the other, okay? Um, I wrote that slide like 10 minutes ago and it's not quite right. I'm going to fix it. So what are these statements that can appear in a proof? You're allowed to put an axiom all the time. These are assumed to be true. You can always use them. If you've already proved some statement, then you're allowed to put that statement in your proof. And the way you create something new is using so I talked about rules of inference. So if you look in the book, they have like a whole bunch of them, but there's only one that you need, and it's called modus ponens, which means the rule of detachment. It allows you to detach from an implication. So look at what modus ponens is. Hopefully it makes sense. If you have already in your proof the statement A, and you also have already in your proof the statement, if A then B, then you can add in your proof the statement B. You can deduce B from A, and if A then B. So you see that how you detach. That's why it's called the rule of detachment. Okay. So if you know that A is true, and you know that if A then B is true, then B is true. That's it. Okay. So formally, that's what a proof is. Okay. Now, I'm going to throw here a bunch of words that you may or may not have seen before. This is what we call meta mathematics. It's a higher level. It's just names. So when we converse and we talk about proofs and math, these are words that are convenient to use. Okay. A theorem is a proof statement. Okay. So that's when we say a theorem, it means something that's been proved. Okay. And a lot of these words in there are actually all variants on that theme. Okay, a proposition is also it's a theorem. It's the same thing as a theorem, but it gets a name that sort of lets you imply that it's not as important as, it's not really called a theorem. It's just a proposition. So like, this is true, but it's not a big deal. Okay, axiom. Um, these are the statements that we accept as true. They are not proved, okay? They are basic truths that we build on. I'm going to show you another document in just a sec to illustrate this, okay? We have to start from somewhere. You can't start from nothing. So you have to have some basic statements that you are allowed to start from, to use to infer new statements, okay? A lemma is a theorem, okay? But we call it a lemma because it is probably going to be used to prove something else, right? I said that when you're doing proofs, you often use things that have been proved before, right? So a lemma would be something that you're not really interested necessarily in itself, but you know that you're going to use it for the proof of some bigger theorem, right? A corollary is something that it's a theorem, so it's a proof statement, but it follows from some theorem that you've just proved, okay? So it indicates, yeah, this thing just follows from what we did, okay? The last two are different. So a conjecture, but this is the same, I mean, this is the same terminology as in everyday life, but in science and especially in math, a conjecture is a statement which is not proved. We don't know that it is true, okay? But people or some experts think it's probably true. Their intuition tells them that this thing will eventually be able to prove it. We just don't know how to do it yet. Okay, so that's a conjecture. Sometimes they turn out to be false. Okay, and the definition was that that's a name we give to some concept, to some mathematical object. Okay, so these are terms that you're likely to see at some point or another, or you may have seen all or part or some of them already. One last remark. To illustrate, I'm going to do proofs. A lot of them will deal with arithmetic, number theory, okay? There are a couple of reasons for this. First, these are things that you know already, and we are going to use that a lot when we reach chapter 4 and to prepare for public key cryptography, okay, which is based on some more advanced number theory that you have not learned in high school or CJEP up to this point. So it'll prepare us for that, okay? A little note on formulation. And I've mentioned this before, that we don't quantify as well to go fast, right? So in first order logic, we have to quantify properly. But in everyday math, you're likely to see a statement like this one. If X is bigger than Y, if X greater than Y are positive reals, so if X and Y are positive reals and X is strictly greater than Y, then X squared is greater than Y squared, okay? It's understood here that X and Y are universally quantified. This statement clearly says whatever reals that you take which are positive and such that X is bigger than Y, it's for all X and Y like that, then, okay? So the very formal statement is the one that I wrote at the bottom there. That's the very, very formal way of writing this, but it's a bit painful. You can imagine if you wrote a whole book like that, it's unbearable, right? So we'd rather use natural language as much as possible, but you have to keep in mind that there is quantification going there, okay? That's important. The rest of this I will talk about later, okay? So I'll finish the slides here, okay? And we're going to go to this bunch of equations or identities, I should say. So I've uploaded this to Leia, okay? And I said we're going to do a lot of proofs involving integers, okay? So to illustrate what axioms are and to refresh your memory and also to give you like some basic things that you know you can assume anytime, you don't need to prove them. I've listed some properties of integers here and real numbers that you should know, you probably know, okay? And that you'll be able to use anytime. So I'm considering these as axioms. In a sense, they are, okay? So I have two kinds of properties. I have arithmetic properties. So these deal with the product and the sum. And I've got order properties on the next page. So I'll just go through them very quickly. So I've put properties for the sum here, okay? The first one is that if you take the sum, the difference is, yeah. But anyway, so the sum and difference of any two integers is an integer. You can assume this to be a true, okay? So if you add or subtract integers, you get an integer. You're not going to get a fraction, right? The same is true for rational numbers. If you add or subtract rational numbers, you're going to get a rational number. And if you add or subtract real numbers, you're going to get a real number, okay? So you can always assume this. Second property is the associative law for the sum. Zero is, so notice also I said that in the little preamble there, but I didn't say for all A, but it said this is true for all A, this is true for all A, B, C. Everything is universally quantified, okay? So 0 is a neutral element for the sum. Every element has an inverse, which is minus A, or an opposite. The sum is commutative. Then product, same again. Everything is closed. If you multiply integers, you get an integer, okay? Associative law, 1 is a neutral element, 0 is an absorbing element. Number 5 is really very useful. We use that all the time. If A times B is 0, then either A or B is 0. This is important. Product is commutative. I put the distributive law here. There's a mixed property of these two. It mixes both operations, okay? You know these. I mean, you use them all the time. You use them in calculus for sure. Here are order properties. If A is less or equal to C and B is less or equal to D, then A plus B is less or equal to C plus D. So the sum preserves the order. It behaves well with respect to the order, okay? The product also, except you have to be careful with negatives, as you know, right? If A and B are greater or equal to 0, then AB is greater or equal to 0, okay? And if A greater or equal to 0, B less or equal to C, then AB is less or equal to AC. And I put a couple more here. The square preserves the order, but again, some of these, I mean, I could reduce the number of identities that I use. Some of them can be actually proved from other identities, but I just threw them there. You don't really need to know anything else. So you see, there's no trig, there's no nothing there, right? We'll never use that, okay? So, okay, so these you can always use. You never have to prove them for sure, okay? All right, so let's jump into 1.7. So let's go here. Where are you? Let's go here. Okay. So, okay. So I'm going to give, as we go along, I'm going to give you also some basic definitions, okay? My first definition, so most of the proofs I'm going to do, and I mean, all the proofs I'm going to do today deal with integers or real numbers with using those axioms there, okay? But I will be fairly informal, okay? So I'm not going to write, at the beginning I might go be a bit more formal so that you see the thing, but after that I'll, okay, so definition, an integer n is even if, I'll use, because otherwise it's just going to take forever, but I will use the existential and universal quantifiers when I'm writing, okay? So if there exists an integer k such that n equals to 2, okay? So this is the definition of an even integer, pair en français. An integer is odd. I could define odd by saying it's not even. I could do that, but I'm going to give you a different definition. So it's odd if there exists an integer k. I'm using the same letter here, but that's fine. That's okay, right? Such that n is n equals 2k plus 1. That's what an odd number is, right? It's one more than an even number, okay? Now, I'm going to state a fact here, and you might laugh or cry depending on the situation. I don't know. Fact, okay? I mean, every integer is either even or odd, but not both. Okay, so I'm going to prove that, but not now, because actually I don't have all the tools to prove it. So, so there are two statements here. Every integer is even or it's odd. This I won't be able to prove until chapter 5. Okay, but the second part I'll prove in about 15 minutes is that no integer is both even and odd. Now you're saying, what the hell is he talking about? This, we know this is true, right? Right, you know, but it's more belief than knowledge, right? If I ask you, well, can you explain why a number cannot be both even or odd, you'll go, I don't know. Or maybe you'll be able to prove it, but you have to prove it, right? So, so you have to be careful with what you know or believe or have prove or can prove, okay? So, but anyway, to illustrate a specific proof technique, I will show you in just a few minutes that an integer cannot be both even and odd at the same time. But I'm going to start with some easier stuff. Okay, so here's our first example. Let's prove that if an integer n is odd, then n squared is odd. Okay, so another way of saying this, the square of an odd integer is odd. By the way, I mean, this is a very simple, little easy proof, but I'm going to be reusing that as we go along. Okay, so here's the proof. Okay, so I start with the knowledge that the integer is odd. Okay, so n is odd means what? I apply the definition. There exists a k, an integer, this is important, such that n equals to 2k plus 1. So far, so good. I want to show that n squared is odd. So I want to show that n squared is equal to 2 times some integer plus 1. That's what I want to do. Okay? So let's try to see if we can do that. I'm guessing many of you can sort of see how to start this for sure. Okay, so you want to say something about n squared, so you square n, right? So n squared, we know n is 2k plus 1. You square that. You see, I'm using all these basic properties. I'm just using the usual stuff that I know, right? So this is 4k squared plus 4k plus 1. Okay. Now, my goal is to show that n squared is 2 times some integer plus 1. So let's try to do that. Let's try to write this as 2 times something plus 1. This is not too hard to see, right? This is 2 times 2k squared plus 2k plus 1. Hopefully everybody is okay with that, right? So let's just give that a name. I'm putting a lot more details here than what we would usually do, but let's call this L. So this is 2L plus 1, right? So n squared is equal to 2L plus 1, where L is 2k squared plus 2k is an integer, right? So if you think back, I mean, if you start with k an integer, then k squared is an integer, 2k squared is an integer, 2k is an integer, and the sum is an integer, so it's an integer. You're fine. You're not going to get 1.73 suddenly, right? Okay, so that means that n squared is odd. And I'm going to put a little square here, which indicates the end of a proof, which is really useful when you're reading a long text full of proofs that you know, because sometimes you read and I mean, you know, you just think back at those things that I've shown you, like in my Adobe Reader, all these things that I wasn't supposed to show you. When I'm reading these proofs in there, sometimes I just go like, is it finished? I don't know. not sure I got it. So, I mean, it's okay. It's supposed to be finished here. So I get it. That's it. Okay. Hopefully that wasn't too hard. Okay. So if you are good with this, I'm going to do a second proof. Is it okay?
Yep.
Okay. Let's do another one. Okay. Let's define a perfect square. So an integer, let's say n is a perfect square if there exists some integer k such that n equals k squared, right? So the squares. Okay. Okay, so here's our second example. Prove that if n and m are perfect squares, so is n times m. So the product of perfect squares is a perfect square. Okay. So these are, I mean, okay, so in the book, if you're, I mean, this is a good place to read the book because I'm not doing probably all the same examples, and they probably put more detail. So it might be give you a different feel for it. Now, what did I want to say? Blank, forgot. Book, perfect squares, n times m. Yes. So in the book, sorry, in the book, they've divided section 1.7 in subsections, which are proof techniques. And now we would be in their section direct proofs. Okay. So in a sense, these proofs do not require any specific kind of technique. You just apply the definition and use your knowledge or, axioms to get what you want. And they don't require a lot of ingenuity. So in a sense, they'd be called sort of almost trivial proofs. But it's really just applying the definitions, okay, plus some axioms. Okay, so I want to show that if n and m are perfect squares, then the product is a perfect square. So I start, so n is a perfect square. That means there exists a k such that n equals to k squared. Okay, I'm going to do something, and okay, m is a perfect square. I look at the definition, it says there exists an integer k, so this is an integer, such that m equals to k squared. Does anybody want me to stop at this point?
Why would they both be equal to the same letter?
Excellent. Okay, and I figured out why my camera freezes. It doesn't freeze, it's zoom. I know exactly what's going on now. Okay. So this is really important. So this is a mistake that I've seen often. You have to take a step back from the names of the variables, right? So the definition of of a perfect square, what is it? It is an integer such that there exists some integer squared that gives you your integer. Now we called it k in the definition because we just gave it a name. You can call it whatever you want. Now this is, I'm going to keep it there. This is bad. Okay. Do not assume n equals to m. Okay, so please be very careful with this. Okay, so when you're applying the definition, you have to think n is a perfect square, so it is the square of some integer. M is a perfect square, so it's the square of some integer. These integers do not have to be the same, so don't use the same letter because you're making an extra assumption that they're equal. That's bad. Okay, so here's what you really want to do. You want to say, so m, so let me just do that. M is a perfect square So there exists some L in Z such that M equals to L squared. So this is, I'm just using the definition. The name of the variables is irrelevant, right? As long as you're consistent. Okay, so this is good, okay? So from this, I want to conclude that n times m is a square. In other words, that there exists some integer squared that'll give you n times m. Now that's the part where it's just your intuition, your knowledge. This is where it has nothing to do with writing proofs, right? You have to figure it out, okay? So how do I figure it out? I mess around on some piece of paper, right? And then I figure out, okay, that's why it's true. Then you write it up, okay? So n times m, this will be k squared times L squared. And by using the commutativity of the product, this is the same as KL squared. So NM is a perfect square. It is the square of some integer. Okay, so that's so some of you might be thinking, oh, there's so little math in here. There's little computation, but it's all math, right? It's okay. Let's move on to some more interesting stuff. Okay, here's finally sort of a connection to what we did in a couple of weeks ago, the contrapositive. Okay, contrapositive contraposition. This is a useful proof technique, okay? It's straightforward, and it's very, 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 very useful. So what is contrapositive? Okay, so remember it comes from this. So if you have a statement of this form, if P then Q, what is the contrapositive? It is not P implies not Q. So you flip it, but you negate both. And we know that's completely equivalent to this statement. Okay, so suppose that you want to show if P then Q. It is completely equivalent to show that not Q implies not P. And in some very, very simple, I'm going to illustrate this by the simplest possible proof, where one of them is like not possible and the other is easy. Okay, so sometimes the contrapositive can be very easy, while the direct proof is hard. Okay, so here's an example, very, very simple example. We're asked to prove that for every integer n, if 3n plus 2 is odd, then n is odd. Okay, so that's what I need to prove. Okay, I'm going to try, and I'm going to illustrate. Hopefully you'll learn something from this. You'll see that if you try to do it directly, you're going to hit a snag. It doesn't work well. Okay, so here's an attempt at a direct proof. Right, so we're trying to show for every n, 3n plus 2 is odd, implies n is odd. Right, so that's what we're trying to do. Okay, so let's assume, so we're told that 3n plus 2 is odd, and I want to deduce that n is odd. So this is odd, so this means that there exists some integer k such that 3n plus 2 equals to 2k plus 1. Okay. I want to conclude something about n. So what about n? Well, look at that. N is multiplied by 3. You're not going to get rid of that 3. Okay. And I'm going to add something here. So again, this is something that I've seen often, and I'm just going to forbid you to do it because it's inelegant and it's going to get you into trouble. I'm just going to really forbid you of doing this. When you're doing proofs with integers, you really want to avoid dividing. I mean, you're just going to get yourself into trouble. Okay. So, and it's just not the right way, the right, man, that didn't sound right. It's not the right way, okay, of thinking. Blah, blah. Okay, so please, when doing proofs with integers, avoid using, I mean, you can divide as long it's not the way. Yes, avoid using fractions. Okay, you just don't want to do that. Okay, so and I'll repeat this when we get to a point where it's going to be perhaps tempting to do that, and you just want to avoid that. And I promise that if you make an effort to avoid that, you will understand things much better. Okay. So here we have 3n plus 2 equals 2k plus 1. We can't get anything on n from this. Okay, this is no good. So I'm going to use the contrapositive. Okay, so we use the contrapositive instead. Okay, so what am I trying to show? I'm trying to show that if 3n plus 2 is odd, then n is odd, right? So what is that? The contrapositive is not n is odd, implies not 3n plus 2 is odd, right? Let's copy this and change slide. So I'm going to prove this statement instead, but it's the same. It means exactly the same thing, right? But it's just technically it'll be easier. Much easier. Okay, so this is what I want to prove. Okay, now saying that an integer is not odd, I said, well, you know, it means it's even, right? So, but I haven't proved that, but I'll show you later. But so this is the same as if n is even, then 3n plus 2 is even, right? That's the same thing. I want to prove this. Okay, and now that's going to be straightforward. Okay, so n is even. That means there exists a k, an integer, such that n equals to 2k. So 3n plus 2 is equal to 3 times 2k plus 2, which is 6k plus 2. And what am I doing? I want to show that 3n plus 2 is even, so it's 2 times some integer. So I just want to factor out 2. 2 times 3k plus 1. And 3k plus 1 is obviously an integer. So 3n plus 2 is even. End of proof. Okay, so you try that directly and it just doesn't, you know, it just doesn't work well. So you try to contrapositive, and just this very simple statement, but the shape of the statement makes it that the contrapositive is just very easy as compared to direct proof. So that's something when you're doing a lot of these, eventually you do it sometimes even without thinking. You just go for either P implies Q or not Q implies not P, and just choose the one that feels more natural and you don't even think about it. Okay. Yeah. Okay. Here's another one. Here's another one. And it's, I mean, at this point, you I mean, this, you're starting out, right? So you might not know at first which is better. So you try one way. If nothing happens, you try the other way. And if that works well, you're done. If it doesn't work, then you have to try something else. But okay, here's another one. If n is equal to a times b, where a and b are positive integers, then a is less or equal to root n, or b is less or equal to root n. This is a very useful little observation. I want to prove this, right? Okay. Now, you look at this thing, and if you mess around a little bit with this, it's not going to happen. It just doesn't really work very well as written. So we're going to try to rephrase it using the contrapositive. Okay, so we rephrase, we use the contrapositive. Okay, so first of all, you have to make sure that you're writing everything properly. So so let's rewrite it this way. So I have a and b integers, but are positive. Then to show, I have to show that n equals to ab implies a less or equal root n, or b less or equal to root n. Okay, so this is what I want to show, this thing here. I'm assuming that a and b are integers and they are positive. Once I've done that, then I want to show this implication. Okay, so now I want to use the contrapositive. So let's write this. So this is negation. I'm using a bit of symbolism here so that you see the connection with what we did a couple of weeks ago. Okay, but if I were, I mean, once we get used to it, we don't do that. We just write the contrapositive. But it's, if there's, like, this one is a bit tricky. There's an or, so you have to be careful. So not a less or equal root n or b less or equal root n implies not n equals ab, right? So this is the contrapositive. Okay, now we have the negation of an or. You have to use De Morgan's law, right? So be careful with that. So now I'm negating, I have an or, and I want to distribute that negation, but I have an or, so it becomes an and. So this is negation of a less or equal root n, and negation of b less or equal root n implies, well, n not equal to ab, right? That's just another way of writing it. Okay, so in other words, this is, so what's the negation of a less or equal to root n? It is a strictly greater than root n, and b strictly greater than root n. This should imply that n is not equal to ab. So this is what I need to prove, right? Okay. So maybe you can see it now, right? So we're almost done. I'm going to scroll here. So suppose a is bigger than root n and b bigger than root n. Everything is positive here. We have a bigger than root n, b bigger than root n. If you think of basic properties of the order and the product, it's in those axioms I gave you. If you multiply both sides, you're still good, right? Then a, b is bigger than root n times root n, which is n. So AB is strictly greater than n. So n is not equal to AB. Bingo. And we're done. That's a cool one, okay? Because I'm using the contrapositive. I'm using a basic property of ordering and product. And I had to use, for the contrapositive, I had to use De Morgan's law. So there's, I mean, this is a really good example where you have to use a lot of stuff that we've seen and that you know, and there's a bit more protein on the bone. Okay. Is that not too bad up to now?
Sounds good.
Dankeschön. Grazie mille. Okay, so we're going to start doing some cooler stuff. Okay, so let's define, although I've given this definition before, but to just refresh your memory. So a real number, R, is rational. So what does it mean to be a rational number? It means it's a fraction, a quotient of integers. So if there exists P and Q integers such that R is equal to P divided by Q. This is almost right. I have to add Q is not 0. Right? So this is important. You can't divide by 0. It makes no sense. So there exists two integers, one of them not 0, such that R is the ratio of these two integers, hence the name rational, as in ratio, as in division. Okay, so if a real number is not rational, it is called irrational. Okay, so that's the definition of an irrational number. It's a number which is not rational. Now, the Greeks for a while thought that these things did not exist. They thought all numbers are rational, and that's all there is. And they eventually discovered that this was not the case. And in fact, if you then move 20th century later, Cantor proved that almost all real numbers are irrational, right? I sort of gave you a little glimpse of that in the talk about Hilbert Hotel, right? So in fact, if you look at the real line, there are almost all of them are irrational numbers. And so let's do a couple of things related to these. So here is a first example. And this was, I put that in the list of axioms, but what the hell, let's just prove that here. Prove that the sum of two rationals is irrational. Okay. So what I need to show is that if I take any R, any S, if R and S are in Q, then R plus S, right? That's the name of the set of rational numbers. Okay. That's a different way of saying it. Okay. So I want to prove this. Okay. So what do I need to do? This is a direct proof. There's no contrapositive here. It's just a direct proof. I use the definition of rational numbers both ways, right? I use it for my hypothesis and I'll use it for my conclusion. Okay. So yeah, R and S are rational means that R is equal to, there exists P, Q, Q not 0, integers such that R equals P divided by Q. Let me scroll here.
I'm sorry, what is the little bar after the R? Is it a 1 or is it an and? What is it? So like if you write R S is element of Q,
Yep.
what is the little 1 after the R?
It's a comma.
Oh, it's a comma.
Comma.
Sorry.
Okay, sorry.
Yeah, yeah, it's yeah, sorry.
That's fine, thank you.
Okay, so R is rational, so it is equal to P over Q, P and Q integers, Q is not 0. And there's also M and N. Notice I'm not using P and Q because I have no reason to believe that R and S are the same, okay? So there exists M and N not 0. These are integers such that S is equal to M divided by N, okay? And I want to show that their sum is rational. So what do I do? Well, I'm going to add them, right? R plus S. This will be P over Q plus M over N. As written, I can't conclude anything. I haven't done anything. I just rewrote R plus S. I want it to be a fraction. So what do? You can guess, common denominator, right? So this will be Pn plus Mq divided by Qn. And you want to be careful. You want to make sure that everything is what you want. So this is a fraction, great. But I need to make sure of two things. Top and bottom are integers. I'm good, right? Because P, N, M, Q, they're all integers. If I multiply them, add them, I get back integers. That's great. And the bottom part should not be 0. Q times N, that's great because neither Q nor N is 0. So Qn cannot be 0. And we're happy, we're done. Okay, so where Pn plus Mq, Qn are elements of Z, and Qn is not equal to 0, since P, N, M, Q are integers, and Q not 0, N not 0. Bingo. It's very, very nice. Pro tip, if you're not using all the hypotheses, maybe something is wrong. You have to be very careful with that. So this is maybe not such a good example, but you see that I've used the fact that neither Q nor N is 0. And I've used the fact that all of these are integers. I really need to use all of this. But when you're doing a proof, if you're not using one of the hypotheses, be careful, okay? So usually they're there for a reason, is because you really need them, that if you remove them, then what's left that you're trying to prove is not true, okay? Okay, here is another one. Prove that if n is an integer is odd. No. Let's do that again. Prove that for every n in Z, if n squared is odd, then n is odd. Now you might say, wait, would we still have to say that at the bottom if we already said it earlier? Let's go back here. You're talking about, oh, the last sentence I put in parentheses. Is that what you're talking about?
Yes.
Okay. Yeah. I'm justifying a statement that I'm making, right? So I'm claiming that Pn plus Mq is in Z. Why is that? Because P and MQ are in Z, and I can multiply and add. I didn't write all the details, but But let's say, for example, the q not 0, n not equal to 0. I'm precisely justifying the fact that qn is not equal to 0. Yeah, I mean, look, on a test, if I give you something like that and you don't, I mean, it's just, I mean, if that would be really, really good if you did it that way. If you didn't write it, I'd be going like, I wish they wrote it, because now I'm not sure if they know why this is true or not. But yeah, you should really justify every. I mean, I'm making a claim here that qn is not 0. Why? Because it can't be 0 if q is not 0 and n is not 0. That's the reason, right? So that's why I'm rewriting it here, to justify that claim I'm making. Does that sort of, maybe not. How can I say this?
No, it answered my question.
Yeah. Okay. All right. Okay. So let's go back to this one. If it looks familiar, there's a reason, because we did something very similar earlier. And if you're saying, oh, wait, we proved that. No, we didn't prove that. We proved the converse. We proved that if n is odd, then n squared is odd. Now I want to do the other direction. So it turns out it's also true. So if an integer is a perfect square and is odd, it means it's the square of an odd number. Okay. If you look at this and you think, okay, I'm going to try to use the square root, that would be the same thing I said. Don't do that, because if you start using square roots and things like that, you don't know what's going to happen. With integers, just all hell breaks loose. That is not the way to go. So here, my intuition tells me go the other way, right? Rather than go from the square to n, go from n to the square. In other words, use the contrapositive. Okay, so proof. We prove the contrapositive. So it means that if n is not odd, then n squared is not odd. Right? That's what I want to say. Now, of course, you can assume, I'm going to show it, but you can assume, of course, it means that if n is even, then n squared is even. So that's what I want to show. Okay.
I have a question.
Yep.
You have to write it in words, or like with the conditional statement and the arrow?
Everything that I've done up to this point, how I wrote it, is fine. You can use whichever you. Okay, so the rule of thumb in writing mathematics, but now, I mean, I'm talking baby boy at the professional level, but still, if we use notation, because at some point, if you write only sentences, it just becomes too long. It's just not efficient. On the other hand, using quantifiers and implication symbols, and only that's too much notation, it becomes very hard to read. It's for a human being anyway. So I would say what I wrote on this particular slide is a nicer way to write it. It's nicer for the reader, right? So they can read and go, okay, I see what's going on. So just if you have too much notation, it becomes harder to read. Okay.
Okay. But
certain
let's
level.
say writing in notation helps us. Can we write it still? Right.
Yeah, absolutely. 100%. Yes, absolutely. Yeah,
Okay.
yeah. That's why on the previous example, I did it that way. It's just because I know you can connect maybe more to what we saw earlier. That's absolutely perfect. No problem. I was talking more about, it's more of a stylistic comment more than anything. Okay, so let's prove this. So n is even. That means we can find an integer k such that n equals to 2k. You see, I didn't write that k is an integer. I mean, sort of clear from context that I mean k is an integer. I should write it. I didn't write it, but okay, let's write it. So now n squared will be 2k squared, which is 4k squared. And I want to show it's even. So I want to say there's 2 times some integer. So this is 2 times 2k squared, where 2k squared is an integer. So Rafael's question here would be, should I write at this point 2k squared is an integer because k is an integer? No, I wouldn't write it here. It's this is, I mean, it's just everything is just way too short. There's no reason to write that. It's clear why 2k squared is an integer. So n squared is even. Okay. All right. All right. Now we're going to hit something. Okay. Notice this. This is useful. Notice that we've proved So we've proved that if n is odd, then n squared is odd. And we've proved that if n squared is odd, then n is odd. In other words, that for every integer, n is odd if and only if n squared is odd. Right? We showed both directions. This way, which is the same as saying if and only if. Okay. Now notice this is the same as, now n is odd if and only if n squared is odd. That is the same statement as, can anybody rephrase it in a natural way? Anybody wants to try? N is
odd if and only if n squared is odd.
Yeah, that's what I got. But can you change it to something else which is completely equivalent?
Well,
And-
like it,
Go ahead. Yeah.
I guess if n is odd, then n squared is odd, and if n squared is odd,
Yeah.
then n is odd is.
Yeah, I
kind
know,
of
and my question is not clear.
Okay.
Anybody else wants to? Has anybody
Not
else?
even.
Yeah, I was going to say n is even if and only if.
Yes, that's what I'm looking for. Yeah, so it's true if you can write odd is not even, but in fact you could write even, right? N is even if and only if n squared is even, because, right? If you have a if and only if you negate both sides, it's still true, because what does it mean? The if and only if, it means that they're both true or both false at the same time, right? So if is the contrapositive of both, right? So this is also true. This is the same statement, but it's useful to write it directly like that. Okay. So a number is even if and only if its square is even, and a number is odd if and only if its square is odd. Okay. So this, think about that. Okay. So this is contrapositives of above statement. Okay. All right. So this is, we've done that. Okay. Now I'm going to show you a controversial proof method. So no, it's not very controversial. Proof by contradiction. So at the beginning of the 20th century, and for some part of the 20th century, there was a bunch of mathematicians, small, that refused the notion of proof by contradiction. And they had valid philosophical arguments against the proof by contradiction, but nobody cares anymore about that. We just use it. It makes sense. In part because if you remove, remarkably, if you remove proof by contradiction, you make your life miserable. Some statements which are become horrendously complicated to prove if you don't have this proof technique. Okay. But the people, the bunch of mathematicians who were against this, they just sort of, because math becomes really painful and boring, and so they just anyway. So what's a proof by contradiction? Okay, so here's the technique. So this is a technique. Okay, some people still try to avoid it for stylistic reasons. Okay, it looks a little bit like contrapositive. Be very careful. They're not the same. Okay, so suppose we can show two things. The first one is we show that not P implies Q is true. And two, we show that Q is false. Okay, so suppose you prove that the statement not P implies Q is true. Okay, and you can prove that Q is false. In other words, that not Q is true. That's right. What can you conclude? Well, if you can conclude something false from not P, it had better be false. Okay, and if not P is false, it means P is true. So we can conclude that P is true. That's a proof by contradiction. Okay, and I'm going to show you some examples and you'll see exactly how this works. Me, personally, I think this makes perfect sense, right? And most people too. But if you conclude something false from a hypothesis, it had to be wrong. So its negation has to be true. That's the idea. Okay. So what I'm going to do here is my first example of this. Okay, so here's an example. This is getting a bit long-ish. So what I'm going to do is I'm going to finish with this, and then next time I will I'll continue with some nice stuff. But here's a first example of this. Show that no integer is both even and odd. Okay, so I announced this result earlier, so it's not very exciting, right? It's not groundbreaking stuff, but I want to show you how we're going to prove that. So I want to show that there is no integer which is both even and odd. Okay. So how am I going to do this? This will be a proof by contradiction. So proof by contradiction. Okay. So what is a proof by contradiction? So let me go back to the previous slide. Sorry. Let's go here. So what do I want to show? It's P. And what do I do is I start from not P, the negation of the statement I want to prove, and I'm going to conclude something false. That's what I need to do. Okay. So let me just, I should add this here. So in other words, starting with the negation of the statement P we wish to prove, conclude a falsehood. Right, so that's the idea. So you start by negating what you want to show. So you suppose it's not true, and you work out 0 equals to 1, for example. So it means that what you started with had to be junk, right? This is the only way this thing is going to be true, right? So your statement you wish to prove is true. Okay, so I want to show that no integer is both even and odd. What is the negation? So suppose the statement is false. In other words, there exists an integer which is even and odd. There exists an integer that is both even and odd. So this is a strange beast, right? Obviously, this is a very, very strange integer. And that's what we would like. We're going to show that it just makes no sense, right? Okay, so let's say it's n. So say n. So it is even. Okay, so it's both even and odd. So there exists a k, an integer, such that n equals to 2k. And there exists, don't use the same k, right? There's an L such that n equals to 2L plus 1. Okay. What is it attempting to do at this point? So basically now you want to mess around with this very strange object and hopefully get something that is nonsense. That's what you want. Any suggestions that we can
Do we make them equal to each other?
Yeah, that's good. So n is equal to n, that's for sure, right? So 2k is equal to 2l plus 1. Okay. And oh, by the way, I'm going to break that rule. That's the only example. But anyway, that I mentioned earlier that you shouldn't use fractions. I'm going to use fractions here. Okay, so now I'm going to solve for 1. So 1 is equal to 2k minus 2l, right? And so 1/2 is equal to k minus l. What's wrong with this? So, okay, I'm going to add a little comment here because you're not going to like me. Say, yeah, he's preventing us from using stuff and he's doing it. Yeah, so here I actually used fractions. Sorry. Don't do it. Okay. Okay, so what's wrong with this statement? Is this statement possible? No, because k minus l, these are integers. So k minus l is an integer, but this is false. This is not true. Since k minus l is an integer, but not 1/2. Okay. So I started by supposing there is a weird beast, which is both even and odd. And I concluded that if that's the case, then 1/2 must be an integer, which is not true. That's false. Could we have just stopped at, yeah. So you stop there and you say, okay, so 1 is equal to 2k minus 2l. You need a kill here, right? So I mean, obviously, I mean, okay. So this illustrates precisely what I meant by one of the difficulties we're going to have is where do we stop? What is obviously true? What is not true? You're going to say, well, in integers, there's no integer which is both even and odd. We all know that, right? Since an even number minus another can't be equal to 1. Yeah, but you see, yeah, I mean, but I'm going to try to avoid asking you questions of this form precisely because of your question. The question was, can we stop here, right? Again, I'll try to avoid this kind of issue because it's hard to say what is the level 0? Where are we supposed to stop? I mean, we could have stopped at the very beginning, right? No integer is both even and odd. Yeah, of course, that's it. End of story, right? So if we're trying to prove it, what we need to to agree on what we will take for granted or not. So here, what I took for granted is 1/2 is not an integer, right? Which, okay, it's between, but yeah, I mean, but again, I will try to avoid that kind of issue because it's annoying and there's, okay, yeah. Yeah. Okay, so I'll just stop with giving you a nice little nice. I don't know if it's nice, but I said you should be careful about proofs by, yeah, to simplify it as much as possible. I mean, we're not going to clear up that the issue of where we're going to be able to stop or not. In a week or two, we're going to reach a point where we'll be able to not worry about that because we'll have proved enough stuff that we'll just assume them, and you won't, the proofs will be at a higher level of difficulty in the sense that we won't be nitpicking with these kinds of little details. I hope you'll see. You'll have to trust me on that. Okay. So at the beginning now, for the first few exercises, it's a bit weird, but it'll get cleared up hopefully. Okay. Yeah, so I said we should, yeah. So we should be, you should be careful not confusing proof by contradiction and proof by contrapositive, which reminds me, I think, second year university. And I had a really very, very bad teacher in an advanced linear algebra course. And he was a super nice guy, but he was just the most horrible teacher ever. And so he started proving, and theorems, I mean, in university math classes are usually, there's a theorem which is stated, and then the professor will start proving this theorem. It might take an hour, it might take 2 classes, 3 classes, it depends on the theorem. Sometimes it might be just 15 minutes, but it can be, the proof of the theorem can be very, very long. So he's proving this, he's working on the blackboard, and, you know, you have these flipping blackboards going up and down, going blah, 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 blah. And at some point, after an hour or so, he gets stuck. An hour, half an hour, I don't remember. But he gets stuck and he's just like, he can't remember, you know, the next step in the proof. And he's just, you know, nobody's helping him probably because he just lost us, you know, 10 minutes or 15 minutes earlier. So nobody's just like, nobody has a clue what's going on. Or so we thought. But anyway, so he's stuck, and he's gonna, and then eventually goes, oh yes, I got it. And then he just starts writing on the blackboard, and then contradiction, we have it. And then some guy in the front goes up, says, but sir, it wasn't the proof by contradiction. So the guy actually managed to get something false from whatever else true that he was doing. So pretty bad. Anyway. That was my little anecdote. Hopefully I'll never do that. Okay, so that's it for today. Next time I will continue with a very nice example of a proof by contradiction and irrational numbers. And that's it for today. I'll see you. If you have questions, stick around, and I'll see you tomorrow.